Hello and welcome to Food Safety Fridays. My name is Simon Timperley from the International Food Safety and Quality Network. Today, our special guest is Sam Rose, Product Line Manager from Eagle Product Inspection, and today's topic is probability of detection with X-ray inspection technology. So, good afternoon, Sam. How are you doing? First time with us.
Very well, yourself?
Great, super. It's great to have you along. Looking forward to a good topic. Where are you joining us from today? You're from the UK, like me. Can you just tell the audience where you're joining from?
Yeah, so I'm from the UK, based not far from Peterborough, if people know that that location. And then the nearest office for me is down in Royston, where I spend a bit, and then spend quite a bit of time over in the US as well.
Very nice. You can see it's quite sunny outside your window there. I'm from up north where it's a bit cooler, but it's the same. Sunny, clear skies, but freezing, freezing cold. So tell us where you're joining from today in the sidebar. It's always good to see. Eric from Texas, I'm sure it's a bit warmer there. Thanos from Greece, Rick from California, Stephen from Kenya. You're all very welcome. I'm going to play the sponsors ads now, and then we'll get straight into the presentation in a couple of minutes. Okay, I'll be back for the Q&A later. For now, I'll hand you over to Sam for the presentation.
Okay, thank you. So, good morning, afternoon or evening to everyone. I see there's a lot of different locations on here at the moment, very different time zones. Welcome to this webinar where we're going to talk about understanding the probability of detection, specifically in X-ray inspection. This presentation will go on to explain how probability of detection, also known as POD, is calculated and why 100% probability of detection is not achievable in a real-life environment. It also looks at factors that affect sensitivity of contamination detection within an array of different products and discusses some of these factors that affect detection, such as contaminant placement, the number of passes, and false rejects created during the testing period. Lastly, it discusses how the latest innovations in X-ray inspection technology are designed to enhance detection performance, while explaining how food processors can ensure probability of detection is consistent throughout the lifetime of their X-ray system. So, as just discussed, these are the topics that we're gonna run through throughout this presentation. The various variables that affect the probability of detection, the product characteristics, types of packaging also have an effect, and they will be covered in some detail. The X-ray system design also has an impact on probability of detection and obviously the contaminant sensitivity that you can achieve. How to ensure probability of detection over the lifetime of the equipment. Obviously need to ensure that the specifications provided last throughout the lifetime of that X-ray solution in the production line. And then we'll wrap up with a little bit of a conclusion at the end. So a little bit about myself. As you now know, my name is Sam Rose and I'm the product line manager for Eagle Product Inspection. I look after the product portfolio as well as applications, project management, sales engineering and the product support teams. I've held various positions within and around engineering within fast-moving consumer goods environments, mainly in the food, packaging and print sectors. I started out my career with a traditional mechanical engineering apprenticeship, sort of hands-on, lathes, mills, grinding, that sort of thing. And followed this through with a HNC in mechanical engineering, a BA honours in business management, and currently studying for my MBA as we speak. So what is probability of detection? Probability of detection can be simply defined as the likelihood of an X-ray system detecting a specific contaminant based on previous experimental data. Such experimental or test data typically involves 30, 50, or sometimes even 100 samples of the customer's product, with a different contaminant utilised as different test pieces. When the samples are passed through the X-ray system, if contaminants are found 100% of the time, this equates to 100% detection rate, not probability of detection. However, finding contaminant 50 times out of 50 passes, or even 100 times out of 100 passes, cannot equate to 100% probability of detection for all future runs. This is because if 100 tests are performed and then the X-ray system is installed and in operation for 10 years, there will be millions of passes during the lifetime of the system, and there is no way of accounting for the subtle variations that will inevitably occur in a real-life production scenario. Just because an X-ray system finds a contaminant 50 times out of 50 passes during a test situation does not mean that for the next 10 years, the system will find that same contaminant 100% of the time. An X-ray equipment manufacturer should therefore never claim 100% probability of detection, as there will always be some variable that cannot be captured in the tests. Some manufacturers state 99% probability of detection. But again, this is a very challenging number to mathematically prove, given the sample size required. This is because in order to claim that 99% POD, a manufacturer would need to have conducted a product test involving 10,000 samples and detected a specific contaminant each time, which is usually unpractical due to the sheer amount of work involved in that. Based on a typical product trial within the X-ray industry, which involves 30, 50, or sometimes 100 passes of the customer's product, it is more realistic for an X-ray equipment manufacturer to state 95% POD. A 95% probability of detection takes into consideration the real-world variables, which are calculated by using plus or minus 2 sigma, which is an industry variable margin of a standard. So as probability of detection is based on detection performance, it is important to explore the variables that affect contaminant detection in X-ray inspection systems. The variables that affect detection can be split into the 3 categories shown on the slide: the product characteristics and the application itself, the types of packaging, the system design, and any changes to the physical parameters with any of those groups will affect how well an X-ray system works and how well it will perform over the lifespan. X-ray inspection works by looking for objects that have a higher contrast to surrounding product. Contaminants, due to the higher density, will usually have a higher absorption than that of the product itself and deliver higher contrast within an X-ray image. The main factors that affect absorption are the chemical composition, which is the atomic mass number, the product density and its depth, the product texture and its uniformity, and where the contaminant is actually placed in the product. The chemical compositions of both the product and the contaminant greatly affect overall probability of detection. Because food products are made up of mostly water, the X-ray absorption of food is then similar to that of water. Food products are usually made up of low atomic mass materials, 16 oxygen and under. By contrast, contaminants typically contain high atomic mass materials and generally have a higher density. It is therefore convenient to use density as the benchmark for contaminant detection in single energy applications. Remember, contamination detection is only possible when contaminants are embedded in product that is less dense than the contaminant itself. Therefore, probability of detection increases when the difference between the atomic mass of a contaminant is greater than that of the product. For smaller contaminants, the greater the difference means an increased contrast and probability of detection in turn. Absorption of X-rays is proportional to the density and depth of the product through which they travel. Therefore, when a contaminant is present in a product with low density, it absorbs more X-rays than the surrounding product. It then appears as a localized increase in absorption or a darker area within an X-ray image, showing more contrast and making it more identifiable. Two examples would be contaminant detection in a low-density bread loaf compared to a block of cheese, which is obviously much higher in density. Both of these items have similar depths, yet very different densities, as you can see in the slide. Therefore, sensitivity within the bread loaf will be better than that within the cheese block. So in two products of equal depth but varying density, the probability of detection within the less dense product will be greater because the density of the contaminant will generate more contrast, making it more easily identifiable in an X-ray image. The example above also highlights how low-density contaminants can be more reliably detected within different products. Due to the loaf of bread being much lower in density, you can see that obviously as it's a lighter grey, we're much more likely to be able to detect smaller, low-density contaminants such as aluminium and low mineral mass. Homogeneous packs are the easiest type of product to inspect, since a consistent product means small absorption changes can be readily detected. Contaminant detection depends on how consistent the product is and how consistently it will be presented. When a product is homogeneous, such as the image above, which can include products such as cheeses, plastic containers filled with various spreads, jams, chocolate spreads, that type of thing, these are very homogeneous, and these homogeneous products can greatly help with adjustment of X-ray sensitivities. Due to the fact that changes in density, which we call grayscale in an X-ray image, are minimal, the operators used within the detection software can be set very aggressively. Ultimately, this ends up with better contaminant detection, performance, and an increased probability of detection. Non-homogeneous products tend to naturally vary in densities. Consider a bag of trail mix shown on the right-hand side, for example. In normal production situation, the trail mix might be slightly thicker, or there may be slightly less in varying locations in a bag. It is also made up of different components, for example, nuts and raisins, which absorb different amounts of energy. When a product passes through an X-ray system, the detector produces an array of successive scan lines of density information that replicate the amount of energy absorbed, and a grayscale image is created. The system then analyzes that image on what it has been programmed to identify and subsequently reject. In a non-uniform product, the power, which is measured in kilovolts or abbreviated to kV, is set to penetrate at the worst case scenario, which is obviously the densest area that will be seen in a normal production environment. Because of this variation in non-uniform or non-homogeneous products, more X-ray energy is required to penetrate or pass through the inspected item. Increasing the X-ray penetration power also reduces the contrast created by the contaminant in areas where there is little or no product, as presented in normal production, therefore reducing its sensitivity. This reduction is because the extra power needed to penetrate the worst case scenario may tend to overpenetrate the contaminant in these less dense areas of the product. This differing density is what affects the probability of detection, and the power difference is how you combat the variance in density. Advanced X-ray technologies allow for programmable power settings for variable product mixes and are capable of adjusting the X-ray power to maintain the same POD for different density products on the same production line. Probability of detection depends not only on the product density, but also contaminant placement. And it's important to understand that this placement will affect the probability of detection value. If the contaminant is outside of the product, say located on the conveyor belt, rather than embedded within the product, there is no product displacement. So contaminant absorption stands alone to product absorption. In effect, overall absorption is lessened when a contaminant is not embedded in the product. Its absorption value, due to the power needed to penetrate the product, will generate much less contrast, decreasing the probability of detection. This can make detecting foreign materials that are located on the belt and not in the product very challenging. This type of situation is only present in bulk, non-packaged applications, such as cereals or meat and poultry applications, for example. Typically, packaged goods would not be affected by foreign materials outside of the packaging itself, as it would not make its way down the conveyor and would probably fall off at any transfer point. Detection levels are affected to a certain extent by placing a contaminant closer to the X-ray source or the detector. When the contaminant is closer to the detector, it is smaller, which also has less magnification, but with a higher contrast. But when the contaminant is further from the detector, the magnification is increased, which makes it appear slightly bigger, but also reduces its contrast. The greatest magnification is seen when the contaminant is located at the top edge of a product, furthest from the detector. It will cast a larger shadow, but again, as just mentioned, generate less contrast. Hence, contaminants located in the center of a product compared to the edge are easier to find due to the higher contrast that is created. With advanced dual energy X-ray technology, locating these hard to find contaminants on the outside or embedded within a product is made much more easier. And a true probability of detection test should be conducted in all locations to ensure its accuracy. Looking at the two images in the slide, they're both obviously blocks of cheese there, which are typically very thick, very dense. This means that the probability of detection and contaminant detection levels vary across the thickness of the product, as previously discussed. This means that to effectively provide specifications within this type of application, contaminants must be seen at the top, middle, and the bottom to factor in the varying magnification levels throughout the whole of the product. If this is not carried out and testing is only provided based on the bottom of the product, the detection levels at the top are likely to be larger in size. This variable is very hard to control, again highlighting the difficulty with guaranteeing probability of detection at higher than 95%. So bringing all of the previous slides together that we just touched on in one example is bone detection within poultry applications. All of the variables discussed previously exist in this one example. As you can see in the image, this includes the differing densities across the chicken breast, its lack of uniformity across the product, the different placement and location of contaminants, as well as the differing density of organic contaminants such as bone, as they're never the same. Different bones have different densities, different ages of birds have different calcifications of bone. These contaminants are never the same. And that also goes with the orientation on the product. All of those factors will affect the probability of detection of bone within this product. With this in mind, probability of detection can be extremely difficult in a real-world example. This is where technology, such as enhanced dual energy, can be used to help reduce some of the aforementioned challenges. This can be seen in the enhanced dual energy image above, where density and product uniformity have been improved to help reliably detect the bone contaminant in the above example, which you can see there is sort of in the center of those two images, and it's easier to see in the right-hand image. With enhanced dual energy technology and image analysis software, we are capable of interpreting different views simultaneously. In applications such as poultry, we typically analyze 3 views per image. This allows us to fine-tune the software along with the operators used to specifically target certain types of contaminants. The example above shows the advanced material filter on the right-hand side, which is specifically used to target low-density contaminants such as bone, low mineral glass, and aluminium. As you can see, the bone fragment is clearly highlighted in the center of that image, whereas the image on the left, you can't see it. You don't know where it is. It's obviously at the point where the 2 chicken breasts overlap. This is where other filter views, which target dense contaminants such as metals easier to find, effectively we create a 3-pronged analysis approach, capturing both low density and high density contaminants in one simultaneous process. Now, some real world examples of the challenges around probability of detection within this sort of environment is very difficult to guarantee probability of detection when you cannot control the contaminant. So typically, obviously, within organic materials such as this, suppliers want to find contaminant that is not stainless steel that has a fixed density. It's a bone where density varies, as I mentioned previously, depending on the type of bone, where it obviously came from in the bird, the age of the bird, the breed of the bird. They all affect that contaminant within the product. Now, when you try to guarantee a probability of detection in an application such as this, how can you factor in all of those changes, all of those possibilities over the millions of different products that get passed through this machine? It's just not achievable to guarantee those 99% PODs or even 100% PODs. You cannot factor in all of those issues. And then it also comes into the way the contaminant sits on the product. Bones are obviously not round, they're not square, they do not have the same dimensions as length and width as they do thickness. So if it's very, very thin but very, very long, it has less density than a very, very thick bone, but a very short in length and width. So all of these factors are obviously uncontrollable and all greatly affect probability of detection. Another variable that affects probability of detection is the packaging type. Obviously, we've just spoke on the previous slide around products that are unpackaged, such as chicken breast, but obviously a lot of products are packaged. An X-ray system creates a 2-dimensional image of all the products that pass through it. Different packages create different challenges. Foil trays can have very dense edges. Metal cans can have pull tabs or lids, which you can see in the slide. And glass jars have metal lids, crowns, and heels, which are also known as the bottom part of a jar. And these can all prove challenging to inspect. And because these parts of the containers will always be present in the inspected image, probability of detection can be greatly affected. Similar challenges can occur with large, tall cardboard boxes, for example, case inspection. The corrugated section of the cardboard, when dealing with these tall cases, can begin to look extremely dense. Obviously, you're X-raying through cardboard that stood upright, that may be 300 mil, and to the Americans on the call, 12 inches thick, which obviously adds some density to that cardboard there. And it looks like that in the X-ray image. You can't take it out from the image, only via software. So these types of challenges can cause issues with probability of detection. And they even occur in sort of the cardboard dividers in sort of thin cases where you've got folded carton rather than cardboard. Less dense, but still present, and can cause challenges. That's where careful setups can be used to help mask out that packaging. So obviously it's there, it's X-rayed, but the software removes it from the image. For example, there's a tuna can obviously in the slide, and the pull tab that's located on the top of it lowers the probability of detection because an X-ray system will see the pull tab as a contaminant. It is a metal contaminant on the top of that can. It is only with the advanced imaging software that the uniform size and shape of the pull tab can be recognized and cut out from the original. subsequently creating two images to be inspected separately. This advanced software then inspects both images for contaminants, and by removing the pull tab, the probability of detection is enhanced for the entire product. This enhancement can be replicated on other varying packaging types, such as foil trays, glass jars, the case inspection that we just discussed. The above application example highlights what X-ray providers can do to improve contaminant detection levels and probability of detection. Using these techniques, we effectively create two zones, but it's important to note that the detection levels and the probability of detection within those two zones will be different. The detection level within the pull tab area is likely to be worse than around the body. You can see that the pull tab is denser, it's a bit more busy, it's less homogeneous, whereas the body of the can is one grey. It's a very simple grey with very little contrast differences. This means that in these types of applications, multiple detection levels and the associated POD should be provided to ensure the highest sensitivity possible. The third variable that affects POD is the X-ray system design. Best practice is use of an inspection machine with sophisticated software that can effectively detect contaminants and increase POD in all variations of packaging for cartons, pouches, and rigid containers. The technology leveraged for inspecting these main packaging types are vertical and horizontal single beam detection systems. Single beam inspection is one X-ray beam shooting through the product to detect contaminants. In applications such as bottles, cans, and jars, a horizontal single beam solution is typically used, and this is demonstrated in the slide. A single beam X-ray system provides an acceptable level of detection in the body of the jar, but may not yield the best results in the base or the top of the container. As you can see in the above illustration, there are two areas highlighted in orange within the glass jar where contaminant detection is severely hindered due to the geometry of that jar. This is typically due to the large amount of material present, causing a much darker area within the image, causing less contrast for any foreign materials that may be present in those two regions. Advanced dual view inspection technology contains a single generator that sits at the side of the conveyor and creates two views out of two beams, which are angled away from each other 45 degrees apart. The beams strike two separate detectors, meaning every can or product is imaged twice. Each image represents a different viewing angle, which increases the coverage inside the container and significantly improves probability of detection in the body of the product, as well as on the sidewalls. This also provides two chances at detecting contaminants, as both views are inspected simultaneously. As you can see in the slide, this type of system design can help improve the contaminant sensitivity and the correlating POD compared to the single view system in the previous slide. By creating two views from two different angles, contaminants are easier to find within the whole of the product, especially within the difficult area highlighted previously. Combination beam X-ray systems featuring up to 4 X-ray beams significantly increase the overall inspection coverage in glass containers, namely, compared to the single X-ray beam or even the dual X-ray beam, by reducing areas with limited detectability and optimizing detection in the most challenging areas, which are the base, the sidewalls, and the neck of the jar. As you can imagine, by having 4 simultaneous views looking in slightly different angles, contaminants are easier to locate. Looking at the image above, you can see how the contaminant appears in 4 different locations. It's just obviously there in the image. I think you can just see it above the bottom crown there. And if you look at them all, they're not in the same place in any of those views. And that's due to the different viewing angles. This can help find contaminants that in one view are not visible, but are within another. The 4 views also greatly help with probability of detection throughout the product, but especially in those difficult areas discussed previously. In conclusion, the system selected should take into account package type to help determine the optimum design for the best probability of detection over the lifespan of the X-ray system. POD should be provided in the different areas on applications such as shown as above, including the bottom, which we call the crown, which is typically the most difficult area, the body of the product, which is typically the easiest area, also with the smallest contaminant specification, and then the lid area, which can be challenging depending on the material and the product portfolio of the jar. These types of applications have further challenges that occur based on the product packaging. Different packaging, such as jars, are often made by various manufacturers, which can and does create different packaging, which includes the density changes of the glass, even to the geometry of the product, of the packaging, sorry. And if this packaging supplied by different manufacturers is ran intermingled, this can severely affect the probability of detection, contaminant sensitivity, and the subsequent false reject rate. When different manufacturers of packaging are involved in a product line, you have to be particularly careful in that they are identical, and if they are not, sometimes different programs have to be created for when you run different manufactured packaging. Now that we've discussed the three variables that affect probability of detection, it is important to outline how food processors can ensure POD is consistent throughout the lifetime of an X-ray system. This is achieved by embarking on a product trial from the beginning of the buying cycle, having a performance validation report, conducting daily routine checks, and having annual preventative maintenance, performance validation, PMPV, service reports. These four factors will help your X-ray machine run optimally throughout the course of its lifetime. We will discuss these in more detail in the coming slides. So, product trial, product testing. This is essential to confirm whether an X-ray system is suitable for a specific application. A product trial should never be conducted using one sample, as this will only prove what can be detected in that one specific sample. The number of samples should be statistically significant, and obviously as well as practical. You can't have thousands of products sent to an X-ray supplier to run this product trial. Equally, a trial should never be conducted by placing contaminant in one location within a product, because where the contaminant is, and obviously how high its up is in relation to the detector and generator, as we touched on earlier, will affect how easy it is to find. Food processors should be wary of a test report that claims an X-ray system can detect the size of contaminant without any explanation of how many product passes were involved in the trial, what the false reject rate is, and that's typically in the industry abbreviated to FRR, and how likely it is that the system will be able to attain this when performing in a real-life production environment rather than under test conditions in a laboratory. A product trial will help to ensure that when an X-ray system is installed at the food processor's production site, the POD stated on the test report is realistic and achievable. Once an X-ray system is installed at a food processor's site, a performance validation report will be conducted by an engineer. This will help determine whether the contaminant test size selected at the initial product trial can be detected in line in the production environment. A performance validation should be carried out for every product type. It should be completed using each type of contaminant that will be used in the routine checks. And these are typically stainless steel, ferrous, non-ferrous, aluminium, and glass. Afterwards, a certificate will be produced declaring the correct test piece size for each product and the X-ray system. The X-ray system will then be tested using this stated size on every contamination check carried out. In addition to validating the sensitivity of an X-ray system, it is important that an X-ray system's operation is also validated to ensure that when a contaminant is detected, it is properly rejected. With proper rejector selection, this can be done by placing a contaminant in different locations, as well as producing successive detection events. Such tests should be performed to a statistically significant, as well as practical number during the installation and setup. A performance validation will give a food processor confidence that an X-ray system is able to control contamination to an acceptable level, and to help ensure POD is consistent throughout the X-ray system's lifetime. Routine checks are essential to ensure an X-ray system continues to operate in accordance with the specified sensitivity standard, the probability of detection, and the correct contaminant detection. Routine checks are also necessary to confirm that additional warning/signaling devices are effective. For example, the various alarm conditions, reject devices are working, emergency stops are working, the safety system is okay, and that all of the installed fail-safe systems are functioning correctly, such as the reject confirmation, bin full warnings, low air pressure sensors. X-ray systems with built-in performance verification routine encourage regular testing and record generation. The test operative simply enters a user login code into the system so the test can be completed with the correct test samples. Hard copy documentation can be provided through a local printer to demonstrate compliance with retailers' codes of practice, making routine checks easier to manage and keeping the system running optimally. Sorry if you can hear my dog in the background. I'm currently taking a delivery, so apologies for that in advance. Lastly, a PMPV, preventative maintenance performance validation, will help to ensure that the future mechanical or electrical problems can be addressed before a breakdown occurs. Sorry, one second. Apologies for that, everybody. So, PMPV. PMPVs are obviously important to ensure that the machine stays healthy and works as it should. This should include regular maintenance as well as the performance validation checks of the X-ray inspection system. These should be carried out in accordance with an agreed service contract. Such a process should typically take place once every 6 to 12 months, and it is required by most major retailers. That being said, there are some environments where 6 to 12 months isn't adequate, such as the meat and poultry industry, where these are carried out maybe 4 times a year, so every 3 months, because they are harsher environments. An engineer will also test the X-ray system against a performance validation report to determine whether the contaminant sizes stated can still be detected in line. Following an X-ray equipment manufacturer's standing operating procedures, their SOPs, and recommendations, as well as having a service contract, will help to ensure probability of detection is consistent throughout the lifetime of an X-ray system. Before we wrap this up, let's take a few moments to sum up, obviously, what we've just spoken about throughout this presentation. Probability of detection does seem like a simple number, but it is vital for food processors to understand its significance and how it is calculated in order to compare different X-ray systems on the market and make an educated choice when selecting a supplier. While a high POD will instill confidence that dispatched products are safe and of the highest quality, food processors should be wary of test reports that claim 100% POD and equally 99% POD, as we've touched on earlier, very, very difficult to prove. POD is also based on the detection performance. So understanding factors that affect the sensitivity of contaminant detection in X-ray systems is key to guaranteeing a realistic POD over time. In addition, food processors can further ensure POD is consistent throughout the lifetime of their X-ray system by embarking on the product trial, having a performance validation report, conducting daily routine checks, and having annual preventative maintenance performance validation service reports carried out. That's everything for me. One final note I would mention is, please, before you leave today, ensure you check out the offers tab, where you can register to download a detailed white paper on understanding the probability of detection with an X-ray inspection. So that will come available, I believe, shortly. Thank you for listening.
Okay, thanks very much. Thanks very much for that, Sam, and Sam's dog. What's your dog called, Sam?
My dog's called Robin, and he's a German Shepherd, so obviously he gets very defensive of anybody coming to the house. And it's my other half's ordered some Christmas presents, so they had to get delivered while I was doing this, didn't they?
It's that time of year, isn't it, where basically you get a daily delivery, more or less.
So yeah, apologies for that, guys.
It's fine. Excellent. Yeah, I've put in the sidebar, like you say, a lot of the content and more content is available in the white paper. Understanding the probability of detection in X-ray inspection of food. In the sidebar there is a button, download white paper. If you click that, you'll stay in the webinar. It'll just open a new window so you can go and download that at your leisure. But we'll also follow up with an email after today with the slides recording, and we'll link that white paper in there as well, so you won't miss it. Okay, so we've got plenty of questions, so let's just get straight into them. So from Alicia, our product has multiple challenges. We have glass with metal lids and variable size contents, tomatoes, jalapenos, onions. Would the X-ray be likely to find a 1.5 millimeter thick piece of plastic, 1 inch square?
Okay, very, very difficult application. I mean, it's a tool application, glass, obviously some of the most challenging packaging to look at. Plastic, as we touched on earlier in the slides, is not a dense contaminant. Caveat that some plastics are dense, but the majority of plastic is not. Even though it is very big, 1 inch square, you may find that plastic actually looks like a void in your product rather than, depending on the density of the plastic, it may end up looking like a void. So that would only be if you're X-raying through the 1 inch rather than the 1.5. So if it's at 1.5 mil thick and you're X-raying through it, there isn't much contrast generated, whereas the 1 inch may be. But again, plastic is a very difficult contaminant in all applications. So I would advise, if that's something you've got, send it in to an X-ray supplier and see what they could do. It probably will look like a void, so they may be able to do something. But again, that is a very tricky contaminant to find. Okay, thanks. Question from Mohammed. Your systems can check the liquid products before detection to detect contaminant in suspension. Does that make sense to you? Your systems can check the liquid products before detection. So yeah, our X-ray machines can detect them before obviously any liquid product. Obviously, most contaminants that are detectable with an X-ray do not float on water, so they would begin to sink. So we would detect them if they are sinking or if they have obviously sunk to the bottom. That would be fine. There's various applications out there in the world where, such as champagne bottles, where they're actually inverted to find contaminants easier in the cork end rather than the bottom that has a big heel. So there's various things that can be done. But yes, we would be able to detect those contaminants. Great, thanks a lot. Question from Christine. What is the probability of finding glass in glass? Back onto glass in difficult locations. So glass in glass is one of the most challenging applications, depending on obviously the jar size and its geometry. Now, the probability of detection in glass is something I couldn't give you a number now. It depends on obviously the size of the glass. The type of glass you're looking for. Typically, when you do glass in glass, you actually break the jar up to create your contaminants, because that's typically the glass that you're going to find in there, unless you have other glass in your plant that could potentially be in the jar. So typically, the probability of detection changes on obviously the size of that glass, and the best way to get those results is to submit it for a product trial. Okay, got you.
So look, another question from Mohammed. Is there pharmaceutical application of X-ray, for example, detecting products in non-transparent injectables?
Good question. We have got machines in the pharmaceutical industry. Off the top of my head, they're typically around tablet boxes, and it's actually looking to make sure instructions are present in the box rather than a contaminant. And there are various other sort of applications where we're looking to ensure components are present. So obviously, X-ray isn't just about foreign bodies. It can also be used to ensure that your injectable has got all of the components in there, the seals, the springs, etc. But yes, I don't see too much of an issue of finding foreign bodies in an injectable.
Okay, cheers. A question from Joanne. For acidified food industry, we use glass jars and whole spices as peppercorns, coriander seeds. Will it be difficult to find other contaminants?
So it depends, obviously, on the product specifics. I mean, glass jars, as we've said, are difficult. They are some of the most difficult products to find contaminants in. Whole spices, peppercorns, and coriander seeds may have an effect. Typically, salt is actually one of the worst ones for contaminant sensitivity. But in tool applications, most products look there are some look very homogeneous, because the glass jar obviously absorbs quite a lot of density, and the products inside don't make too much of a difference. So I think that's something that you should submit in for a product trial, and I think it should be fine. We've done many applications such as that.
Okay. Mohammed, foreign body detection, is X-ray or metal detection more effective? Always comes up this question.
Yeah. So I guess there's two parts to that question. One, what is your product packaged in? Obviously, if it's metallized, then you're going to go for X-ray. And then second part of the question, are you only looking for metal detectable foreign bodies, the magnetic metals? If you aren't, and you're looking for the glasses, the bone example that we touched on, then obviously metal detection isn't going to do it. And I think typically with X-ray, depending on obviously the product, it's very product specific. You can get down to 0.5 millimeter stainless steel in a lot of products. And I think it is more sensitive, and it gives you a fully comprehensive inspection solution for all contaminants, not just the metal detectable ones.
Okay, a question from Mustafa. Is there a special accreditation for the calibration of X-ray detectors? I mean, are they even calibrated as such? Maybe you can tell us a bit more.
So I'm not sure what that question means, but I can give it a punt. So X-ray detectors themselves obviously are manufactured, and they'll be certified by the manufacturer, depending on who that is. The accreditation for the calibration, there is different rules and regulations around X-ray in different environments where you have to have some accreditation to do that in certain places. But the X-ray detectors themselves, I don't believe are. They'll obviously be certified by a manufacturer. Certain detectors are calibrated. So the dual energy stuff that I mentioned a few times in the slides, they have to be calibrated to get the best out of them, because they're not a conventional X-ray solution. They split high and low energies to make it easier to find low density contaminants such as the bone. They have to be calibrated, and that's typically done by the manufacturer. So as in the X-ray manufacturer.
Okay. Bit of a long one from Pratik. We use aluminium clips to clip the ends of ham logs. Can X-ray differentiate between broken aluminium clips within meat and the actual clips? Also, can it detect bones as well as other contaminants at the same time in the meat?
Yes, absolutely. There's many applications out there, from sort of chub applications. I assume this is a chub with two aluminium clips either end. And what X-ray can do, it can detect those aluminium clips within the product. It can also do count functions, so it counts two clips. If the two clips aren't present, it will also reject the product. So in theory, you'd detect the clip if it's in the product, and you'd also reject it if one clip is missing, or you have 3 clips present, 1 clip present, it would reject it. So yes, and then with regards to the bones, yes, they can be, depending on obviously the density of the bone, but yes, they can also be found at the same time.
Okay, another quite a long one from David. None of the trade body or customer standards refer to metal test piece sizes. Is there a risk assessment or an official guideline of what size of test piece to be used for a specific product? In my case, it would be pork and chicken sausages with 40mm high trays. The weight range between 300 and 1200 grams. Or should we just go with the X-ray equipment's manufacturer's recommendation?
Okay, good question. What I would say on that is there are different guidelines. There's no sort of standard for it. In Europe, typically what was used was something that's called supermarket specification, which is for a large supermarket supplier, and their statement was 1.2mm metals. Now, I think the thought process behind that is 1.2mm metals. If you chew on them, you would not know you're chewing on them. So it's obviously safe to consume at that point. However, many suppliers, many customers demand much lower specifications than that. And I can give a recent example where it's a meat product similar to yours, and that customer is demanding 0.7mm stainless steel. So no to the answer of the guidelines. They're normally driven by the supply chain. So normally there's someone in that chain who's saying you need to detect X size contaminants. But there is no real true rule or guideline to that.
Okay. Pratik's asking, does X-ray work with frozen products?
Yeah, yes, it does. Yeah, absolutely.
Okay.
There's very small differences, but yes, it does.
Okay. Alicia, with Costco implementing X-ray technology into their audit requirements, do you have any advice for manufacturers who use those difficult to detect items, plastic, glass, and spices when other control points are already in place?
Yeah, so obviously very aware of the Costco initiative that's ongoing. Obviously, there's many different rules and regulations that they're using right now, and obviously a lot of that is around X-ray. Do you have any advice for manufacturers who use those difficult to detect items? Plastic. So plastic in X-ray is incredibly difficult, and only recent innovations in the X-ray business has made plastic somewhat achievable. Plastic, rubber can be achieved in certain applications and at certain points with certain technologies. Standard X-ray technology will not find plastic unless it is very, very dense, which typically you don't come across. Glass is doable. It depends on obviously the application itself. Glass can be found with X-ray. The spices, obviously, I'm not sure what that is because you probably wouldn't want to be detecting those, but they can be sort of avoided. So I would say if you've got some demand for that, reach out to your X-ray supplier, and they will be able to do tests for you on those applications with regards to your specific contaminants.
Okay. Another one from Mohammed. Can X-ray detect glass contaminants and other contaminant like bromobutyl closure?
No idea what that is, so I have to defer back to that one after this. I don't know what bromobutyl closure is. Sorry.
Okay, we'll follow up with that afterwards then. Let's have a look. Not too many. Question from Nithin: how to conduct validation of the X-ray machine? Okay,
so validation is typically down to the food processor. Typically, how that's carried out is you have a set number of contaminants, types of contaminants that you wish to detect, and to keep that small, we'll just say stainless, ferrous, and non-ferrous. Typically, you would have those as test cards, and the normal sort of process is once an hour. They're put into product or on product, top and bottom. They're run through the machine. You make sure they reject them 5 out of 5, 3 out of 3, 10 out of 10, depending on how you want to do it. You make sure they go in the reject bin, and you repeat that process every hour from a quality perspective. In most X-rays software, there's a button you can press for validation mode, and it will also save those images, so you've got traceability through the validation as well.
Okay, not too many left. David's asking regarding metal detection, is an X-ray system more reliable than metal detectors? I'm not sure whether he's asking reliable in terms of finding, detecting, or actually stable in running, being able to run.
Yeah, I wouldn't comment on the reliability of the two. I mean, X-ray technology is obviously more complicated, so you can take that. There's probably more to go wrong, but obviously it's much more usable as a full solution. If you've only got metal issues, a metal detector will probably be fine, and obviously at a much lower cost point. But if you've got those other concerns, then an X-ray system is the best way to go.
Okay. Nathan, what is the POD for hot filled products like ketchup in 70 to 80 degrees Celsius?
Okay, so hot filled products don't typically have too much of an effect. Obviously, you have to take into consideration the ambient temperature around the machine to ensure there's adequate cooling for the X-ray unit. But the heat of the product wouldn't typically make too much of a difference. And obviously, for most ketchup, I would assume that the majority of it is in plastic. Yes, there are some glass. So those types of applications are fairly straightforward and very homogeneous.
Okay, and one more here, from Mohammed again. Can X-ray be set to detect multi-type contaminants at the same time?
Yeah, absolutely. So an X-ray system is always looking for all of those contaminants at the same time. So in standard X-ray, you have a single energy view, and those operators used in that software are looking for contaminants. So they're looking for density differences. They don't differentiate between metal. They don't differentiate between glass. They just look for a certain criteria and they reject it. Now, so one operator may tag stainless steel. It will also tag low mineral glass and aluminium, for example, and stone. Whereas when you get to being able to somewhat differentiate between what you're tagging is when you use dual energy. And dual energy, as I mentioned in the presentation, where we look at different views, those different views give you an indication of what you're detecting, because different types of contaminants react differently in those different views, the way we filter them. So, for instance, when you find stuff in the images we showed earlier that I called the advanced material filter, chances are if you see something in there, it's a low density contaminant, such as bone, aluminium, or low mineral glass, and there'd be a different view where you're more likely to see stainless steel. So that's where you can differentiate between them, and they have slightly different targets. But in general, single energy X-ray applications, which is the majority of them, one operator will tag all contaminants.
Super. Right. I think we've got through all the questions. That's very good, because we've literally got a minute to go. So perfect timing. Brilliant. Thanks for your time today. There was some comments in there, praising you for a great presentation, etc. So excellent. First time with us, Sam. Enjoyed it, and hope you'll be back with us again soon.
Thank you. Thanks everyone for your time.
Cheers. Thanks a lot. Okay. I'm just putting your certificate in the sidebar now. We'll be following up with an email shortly with the recording slide certificate, and we will link to the white paper again that we did put in the offers earlier. So thanks for joining today. Great conversation, and thanks for engaging with that, and have a nice weekend, and we'll see you on the next one. Cheers. Bye.